Okay, we look at this example. You would like to fit x and y and find the data of x and y. This line is data of x and y. Data of x and y. That's into y go to beta 0 plus beta 1 x1 plus beta 2 x2 by Excel. And also you can use the data there is no regression in this computer. Okay, for this there is no data analysis in this computer, and also you can ask it to option again. That's fine. If your Excel no data analysis, you can go to option and ask it, but they are already in Excel. Right. And then you add the analysis to pack for this. Right. Analysis to pack for this. Okay, we call this data analysis for this computer. Right. And also you click data analysis. It have many specific. And for this case, we use the regression. To use the regression. For this, we input your y data and x data. This is y data. Collect y. Enter. Right? And also x data. X data, you should both of this column. Right? Both of this column. Enter like this. And also, we would like to show the confidence interval is 95 confidence interval and create a new worksheet. I use EX3 tool, right? And also, we would like to plot the residual cost, line fit cost, standard cost, normal cost, every one. You can plot all this as well. And then you click OK. Okay, this is the new one is EX3.2. This is all data. This is the summary of data. R squared, attack R squared is about 0.97. At the top to you, you should attack R squared is less than R squared. Right. And also this is for regression. We have some equation to define your data for this, yes, because the p-value is very low compared to alpha. Because you calculate based on 95%, alpha equal to 0.05. And this is p-value is about 1/90. It's very low value. Okay, we have some linear equation can describe the data. Right? And also the next step, we check each constant. Right? For x1, for x2, for intercept is 2.26. It's the same, the Excel that you saw previous, the same answer. Like this is 2.26, 2.7, 0.72. Okay, the same. It's approximately the same answer. Okay, this for beta 0, beta 1, beta 2. This is the standard error of this. Is the T and P value, right? So, and this P or P value less than alpha. Less than alpha, that means you reject x0. That means mu0, mu1, mu2 is not equal to 6, right? For this case. For this, and also we have the confidence interval for each constant. This is the confidence interval for each constant. This is the predict value. The predict value of this is the fitting equation, and the normal curve is equal to linear. It's not perfect linear, but it's equal to linear. And then we got the y and x for this. This fit curve is the fit curve. They said the orange one is predict, the blue one is the observed data. For this, this is some the residual is around 0. This is the around 0 also. This also 0. That is the perfect because your data is accurate to describe by this equation. This is based on the Excel. This is based on the Excel. How about Minitab? I will shift to this computer. Okay. For Minitab, right? to apologize for today's maybe my comment is not perfect. Okay, I will share. For example, this is example 8. I think the main we go to the linear. We get an option for that. Let's open Excel. For the Minitab, we go to okay, we will show you later. The next week for data. Okay, we look at the Minitab for linear programming. As you go through the same, but you go through the linear regression. But for this case, you have to respond only y, but predictor we can add x1 and x2 as in the Minitab. And I think it is it. But for this case, you can assign x1 and x2 in for this case. And then you can check this is the degree of freedom for regression. Like regression, the p-value less than alpha. Okay, we have the linear equation that's defined for this. And this is adjust R square, and this is the coefficient. That's why we have the p-value is the same except this is p-value of beta 6, p-value of beta 1, p-value of beta 2. You found that p-value less than alpha, reject S0. That's right. Reject S0, that means except S1, beta 0 is not 0, beta 1 is not 0, beta 2 is not 0, right, for this case. And this is the equation for that, right? It may be for next time I will show you the Minitab, but my complex doesn't work. It's die. Bây giờ đâu nào? Is it about 5 or 6 years? 6 years, it's very old. Okay, and also you can calculate the confidence interval on each constant. As like in Excel, you can find that the confidence interval on beta 1, on beta 0, on beta 2. You can do that also. The same as the simple. Calculate this based on T statistic, right? T statistic. If you calculate by manual, right? In this term, you get like the upper limit, and you minus this term is also the lower limit for this case. Right? Which is this we call the standard error of the regression. And also, if you would like to predict a new value, right? On the mean, of course, sorry, this for the mean. Previously, the confidence on the constant beta, right? You would like to calculate the confidence interval on beta 1, beta 2, beta 0, or the coefficient. You use this formula, right? If you would like to calculate the confidence interval of the mean, that means the confidence interval of the regression line. That's right. The regression line is reading from the mean value. You would like to 95% on the mean. You follow this equation. Right? This is the lower limit. This is the upper limit. Right? Lower limit, upper limit for this. And also, if you would like to predict a new observation, you follow by this equation. This is the confidence interval for new observation. It's the same as I will do talk about a simple linear equation. This is for multiple linear equation, but the equation quite complex compared to the simple. Yes. At the Excel, I showed you previously, show you the lower upper limit. This is lower upper limit of the intercept, right? Is the beta 0, beta 1, beta 2, lower upper, right? Okay. Lower upper, right? And also this by manual, you can calculate for that also. Right? This is the mean value, right? Okay, this is for the PD value. You can calculate this by manual, or you can use the Excel or Minitab to show you, right? For the Minitab, so after you fit the curve, like if you like to predict the observed or the new value, you can go to the regression and predict. That's right, and predict. That's the same as the simple regression. That's right, this is a predict. Would you like predict at x1, x2, you substitute x1, x2, and then you can calculate the new observed. That's right. For that, this is the 95 CI and PI at this value, for example. And also, if you would like to calculate for all the confidence interval of the mean, you can choose all of this is x1 and x2. You do not substitute x1 and x2, you substitute in all of data. This is x1, x2. Show the regression equation and show the PD table. And also, this is the PD. Confidence interval. This is the PD value. This is the confidence interval. Minimum, maximum. This is the predict value at new observation. This is the confidence interval of the mean. This is the predict a new observation. That's right. Predict a new observation. Like this. And also we show the residual part. That's right. This found that the residual is not pattern. Normal is equal to normal. You can conclude that your technique is accurate for this. Accurate enough for this. Again, I will show you this again next week on the Minitab. I would like to take something. And also for this case, you can apply this technique for polynomial regression, like polynomial regression. For this, that means you can convert from polynomial to linear, right? Polynomial to linear. For this, we can use the polynomial to linear based on this technique. Right? Because we have like x square is maybe x1 and x2, right? For that case, x1, x2, x3, x4, x5, for example. This is from non-linear because for polynomial is non-linear. That's right. Polynomial order 1 is linear. Polynomial order greater than is non-linear. That's right. This is polynomial order 1. That's right. This is the polynomial 1 for that case. And order is greater than 1 is non-linear, but you can transform from non to linear, right? For change the variable for that case. This is we have some x and y. For this is we fit with the polynomial because when you plot y and x, it's not linear. Right? It's not linear for this case. And also we transform from y to beta 0 beta 1 x beta 1 1 x squared. And also we consider x squared is x2, for example, like that. Y x beta. This is a previous technique. But for this case, we transform x squared is the x1 or x2, right? Then you can solve this is I use the x1 as x, x2 is x squared, right? X2 is x squared, like for this. And then you follow the same technique. We only convert or change the variable of x1 equal to x1, x squared equal to x2. This is x squared. Right? This comes from this square. 20 multiplied 20, you get 400. That's right. And then you fit this multiple linear. But this is polynomial. That's right. But this is the multiple linear. Right. Okay. For this, we have the p-value for regression is less than alpha. That means polynomial can describe the data. That's right. Can describe the data. And this is the quotient beta 1, beta 0, beta 0, beta 1, beta 2. Right? And p-value is less than alpha for all. That means not 0. That's right. Beta 1, beta 2, beta 2 is not 0 for that case. And also we have the upper and lower limit for beta. Right? This is upper and lower limit for predicted value. Right? For this. Okay. For the next slide, we talk about some categorical regression and indicator. For this, we have mix between quantitative variable and qualitative variable. We mix together. For sometimes we have the value in numerical, but sometimes we have the qualitative. But this is the number of people 1, people 2, that's right. And catalytic 1, catalytic 2. For the case, you can fit with your data. You have to convert qualitative into code number. That's right. It may be catalytic 1 is 1, catalytic 2 is 2, for example. It's level 1, level 2, level 2. The people 1, people 2, people 3, material 1, material 2, material 3. Okay, you represent by 1, 2, 3. And then you can fit together with the qualitative and quality. That's right. For that case. Because this is the categorical regression. For example, x equal to 0 if we observe from operator 1. X equal to 1 is for operator 2. We have 2 operators. We have 2 operators. We would like to fit for this. Okay, we represent operator 1 is 0. Operator 2 is 1. That's right. You have the data from operator 1 is maybe 20 data, for example. That's right. You have 20 data. And operator is 20 data. Also, exactly like this. And also this x1, x2. If 0, 0, what does it mean? This is from operator 1. 1, 0 is from operator 2, but 0, 1 is maybe operator 3, for example. Like this. Okay, for this mechanical engineer, I check the surface of metal part. Right? Okay, we have some data entered in this table. This table you have the number of observations. We have 20 observations. We have 2 types of cutting tool, right? 2 types of cutting tool. This is 302. Right? This is 416. 2 types. And also these 2 types we have the YI and RPM at different values. That's why this is we have two systems. This system 1, system 2 at different pattern 2. Right. Okay, this is the set of data. This is a response surface. You value R, you value R, and you get Y, and you value also you value R, and you get Y. But for this data for 2, 1, this data for 2, 2, for example, like this. Okay. For this case, we represent x mean RPM, right? X mean RPM. X1 is RPM. X2 is for the type of 2. X2 equal to 0, okay, for TO2. X2 equal to 1 is for 416. Right. We have 2x. X1 is RPM. That's right, the speed. That's right. And X2 means the type of the 2. Right. X2 is equal to 0, that means TO2. If X2 equal to 1, it means 416. Right, for that case. This is for the equation if X2 equal to 0. You get this equation is linear, right? If X2 equal to 1, you get this equation, for example, like this. Right. Okay, then we generate the general equation y equal to beta 0 plus beta 1x plus beta 2 x2. And this again, x2 we have to, x2 is the 2 TO2 and 2 416. Right? 416. You can fit this also. Right? Like we fit the same. We have metric x, metric y. Right? We have metric x, metric y. And for this case, we solve with the Minitab. With the regression model. We shoot x1, x2, right? x1, x2. For this case, the data you should like this. This is okay. Right. This is what we call the beta 0 x equal to 1, right? Beta 0 x, and this is beta 1, beta 2. This is data set for 2O2, right? 3O2. 3O2 because x0 equal to 0, right? X0 equal to 0. And then you represent by this is 0 for x2, right? And then for 416, x2 equal to 1, this 1, right? This one, and this is the x1, right? This is x1, and this is y. That's right, this set for 302, this set for 416, right? And then you fit it the same technique. Right? This only represented by x2, we have two types. x2 is 302 is 0, and x2 equal to 1 is for 416, like this. And also you can fit the same technique. The regression model, the response is y, corrected x1 and x2, like this. Also this we have the regression if t value is less than 0, right? This is we have the linear equation fit the data, and there is no lack of it because alpha is greater than period greater than alpha, and then we have the coefficient for beta 0, right? Beta 1, beta 2 for x1 and x2 for this case. This is for constant, right? This is for beta 0, right? This is for beta 1. This is for beta 2, like this. This is we can about p value is very small, like that. Okay, for this. For this is you fit the equation, right? This is the equation is this equation, and also it's the same like this for Minitab. Right. You can find it if you substitute x2 equal to 0. Right. You can check x2 equal to 0. The y value should be equal to this. Right. You can fit by this equation. If you get by x1 equal to 1, right, we do this, for example, like this. You can use this to describe for both type of the equipment, like this. This is mix between qualitative and quantitative, but you have to convert qualitative to quantitative. It's 0 and 1, for example. If you have xt 0, 1, 3, 0, 1, 2, for example, like this. I think this is the next topic. I will talk about the method to find the best loop when you fit the equation by the program, what the technique program to find the best equation by technique. Right? Because this is you can find it when you talk in the Minitab, because it's stepwise in the bottom. Right? In the Minitab, we have some stepwise bottom. In Minitab, we have to this, right? We have some model option and this step one. What is this in Minitab? This is the technique to find the result, to find the solution. Like that. The selection and variable model. What is that? We talk in conclusion. We have like this. Okay, we have this term to predict that, like before this phase is the model that has small value pairs are preferred. This is another value to check. You can check based on R square or adjust R square. You can test based on P value, like or F0, or you can check with the place value. But there's many techniques. Right? Like for the regression, we have stepwise regression, we have the forward recheck selection, we have backward, we have 3 types of the technique. Like the stepwise, what is the stepwise? The stepwise, this is the iteration. That's we have to add in or remove some variable. That's we can add in or remove some variable. And then you check the F in, F out for that case. Like for integral step, if you check you can check F value or you can check P value. Now, you check the value x1, x2, x3. Right? Usually we check P value. If P value is the biggest, that means you can cancel that because there is no effect. If you P value, you can check the biggest. If you check the F value, you can check the minimum value. If we have 10 variables, you check the P value for each. And then you can cut off each variable. You check on P value, you check on F0. That's right, for that case. This is for the step 5. But for the forward, for that case, we look forward. But we start with an empty model. For this case, you do not model. You check the F or P value first. You check the F or P value first, and then you check which P value is significant. You add that variable first. That's right. And then you check the P value again. If the P value is significant or less than alpha, okay, you add that variable. That's right. For that case, if we have x1, x2, x3, x4, we have beta 1, 2, 3, 4, for example. And then you compare P value of beta 1, beta 2, beta 3, beta 4. Which one is the lowest? Okay, you choose that into the model first. And then you check again by model again. Beta 2, beta 3, beta 4, which one is the smallest? And then you include into one model like that. Step by step. If the P value is greater than, okay, you cut off the model. Sometimes you have x1, x2, x3, x4. Sometimes the model is y equal to beta 0 plus beta 1, x1 plus beta 2, x3. No x2 and x4. Because x2, x4 not significant. It's possible, but it's the technique forward. And backward. What is backward? The backward means you model full of or variable first. That means you model the side or of full, and then you check back with P value is the biggest you cancel off. The biggest you cancel off step by step. That's not for this case. Again, the forward you cut off with you not model. You check your P value first. Which value is significant, okay, add to model. But for backward, you make a full model first, and then you check each variable. Which variable is the P value is the highest, you cancel or cut off the model. And then you model again and check the remaining with variable is if the p-value is higher, okay, you cut off, okay, that's right. Until you get the p-value of the variable is less than alpha, okay, input in your model. Because when you do the experiment, we have many parameters. It may be temperature is x1, pressure is x2, pH is x3, speed is x4, level is x5, and then you check all of this affect your response or not. But sometimes x1 no response, no effect. But for this case, you check the model. That's right, you check the model. That means beta 1, beta 2, beta 3, beta 4, beta 5 equal to 0 or not. It's the same. If p-value is less than alpha, okay, it's not equal to 0. If p-value is greater than alpha, it's equal to 0. Okay, you cancel it based on backward or forward, like that. And all this, the Minitab found in Minitab, you can click on Minitab in the stepwise model. Like for this, we have about 1, 2, 3, 4, 5 variables. This is we use testing about 38 brand of union Y, the Y test. We test the test of Y. Like it depends on many parameters. It depends on the Y is the quality of Y. We have 5 parameters that affect the Y. It's quality of the Y, aroma, that's fine. We do aroma, and body and flavor and oakiness. I don't know what is oakiness. This is you test the quality of wine ก็คือรสชาติหรือคุณภาพของ wine the quality of wine depend on x1 quality x2 aroma x3 body x4 flavor and x5 oakiness that's right oakiness. Okay, you would like to model this all of this effect or not, but sometimes parameter is not effect. You can cancel that. That's right. What is that? You do this by the linear model, multiple linear model x1, x2, x3, x4, x5, and quality. Also, you fit this is y and this is x1 until x5. This meaning that not minus this is x1 to x5 because we collect c1 to c5. It show only x1 and this is from x1 to x5 column. Okay. And then you select stepwise. If you select stepwise, and data will show in this. Data will show in this. This is step 1, step 2, step 3. Only 3 steps. If you select the forward, this is you select forward. Because in this we have the three choice. Yes, we have 3 choice. We click this. We have step 1, forward, backward. For the first, you click step 1, and it shows from step 5. That's right. And this is you click for forward. Right. This forward, the forward is built full of option first, and then cancel step 5. The forward is you cut off the step 1. Step 1 only x4 important. This step 1. Step 2 we have x4 and x5. And step 3 is x4, x5, x2. And another is not significant. Only 3 steps for this. Right. Only 3 steps. You get that x1, x4, x5, x2 is significant. For backward, the backward we should full model first. This is all of parameter inputs in model. Right. x1, x2, x3, x4, x5. That's right. For the second step, you cancel the maximum. For that, you cancel x3 first. Right. And step 3, you cancel x1. No step 4 because this is p-value is less than alpha for that step. This is the 3 technique that we can use forward, backward, and stepwise. And also give the same result. Give the same result. You found that the x1 and x3 is not significant affect the quality of wine. Only aroma, flavor, and oakiness affect the quality of wine. Okay, this is the some forest. Okay. Okay, maybe I will show you some technique by Minitab for next week, and also the next week I will introduce you about the non-linear. That's fine. If you don't like to transform from linear to non-linear, you can use the non-linear fitting in Excel and Minitab. In Excel, I will follow by the solver, right? But in Minitab, we have the non-linear regression in Minitab also, like that. And this I will show you next week. Right. Okay. Sorry, some problem. Not my computer doesn't work. เหลือที่น่าจะได้คอมใหม่ไม่รู้ไม่พร้อมเงียน